Let's look at a few simple examples of applications. The examples we could use really range through all sorts of fields and all sorts of levels of difficulty, but let's just look at a few very simple ones that are easy to understand. So for one, you could have what are called social graphs. So for instance, Facebook or any social network would be very interested in this sort of graph, in building these graphs. And these are how they come up with things like suggesting new friends and so on, is by building a graph like this and then looking for edges that they might expect to be there that aren't there. They might say, well, you know this person, but you haven't connected with them yet. And they can infer lots of things by looking at a graph of connections like this. So let's say, for example, we draw something like this, where we have some people. So let's say we have somebody named Linda, Brian, just for examples, Deborah, Fred, and Yvonne. And then we can draw some connections among them. So let's say we have a graph that looks like this. Let's put one here. So at the moment, you might imagine that one of these connections means that these two people, say, know each other or are friends or whatever. But really, you can set up your edges to describe whatever you want. If you were drawing, for instance, an org chart for a company, you could have arrows that describe or edges that describe who reports to whom, and you might have them be directed with arrows. We could even add direction to this. Let's say I start adding some directions, and you might wonder, well, what's the direction here? How do you have a social graph with direction? And one example is if this is what's called an influence graph, and the direction of these arrows could represent the influence that one person has on another. But really, you could draw these arrows to represent other things as well, but whatever makes sense in the application. So if you drew it without the arrows, then you might think it's just that these two people are connected somehow. With arrows like this, you might think these people exert influence, or you might think these people report to this person in an organizational way. Whatever the application is, you can draw it similarly. So it really depends on what the application is as to whether you want to make a directed graph or an undirected graph. You may have heard of the 6 Degrees of Kevin Bacon game, where you try to find connections between celebrities who've appeared in movies together and so on, and look for how few connections it needs to get from one person to another. People say that you only need a handful of connections to connect any two people on Earth, which may or may not be true. There's no proof of that, but certainly people are very connected. So social graphs just have a description of how people are connected in a group. Then we have another application would be like communication networks. So these could be computer networks, they could be phone networks, they could be telegraph networks, theoretically, really anything, any connection that you have. So let's say, for a few examples, there are phone networks, there's the capital I internet, and then smaller internets, intranets, and so on. All sorts of applications of networks like this. So just a really quick example, if you have a LAN, local area network, you can set this up in a variety of ways. I'll give you a couple examples. You could draw a graph that looks like this, where you have one node at the center and then radiating outward to outer nodes. And so there might be sort of this client-server idea where you have one central server, and then the ones around the edges are all clients that are receiving information and sending it back and forth. So if this node wants to send a message here, it has to pass through this central server. That's what we call star topology for obvious reasons. Looks like a star. So if you think about even building, say, like a chat app where you have people can send messages from one to another, you could have something where people can send messages directly to one another, or more commonly you might have where you set up your server, and if two users want to communicate, those messages all pass through your server. So for instance, Gmail or any webmail system probably is going to work like this, where you have emails that pass through your servers. Something like WhatsApp, same thing. The messages pass through your servers, which brings up questions of privacy and encryption and all sorts of things. But it's a relatively common architecture where you have sort of the central hub, and then out connected other clients connected all to the central hub. Another setup you might see is one like this, where you have what's called a ring topology. And that would be if now to send a message between any two, you would just find the shortest route in one direction or the other. And again, there are a variety of options you could use. You can use a hybrid of the two. You could really do any number of things with your network setup. And there are trade-offs to each of them. And then you have to think about how to traverse the network, which is an interesting question of how do you build or how do you carry a message from person A to person B in the most effective way. And it might not be the shortest path. The shortest path might be busy. You might have a lot of messages traveling on one section of the shortest path, and so you might take a slightly longer path because it kind of gets you around the congestion and gets there faster. You can kind of think of it as if you're driving, you might take a longer route to avoid traffic. Same idea on a communication network. If you are looking to carry a message from one person to another, you might bypass some busy sections. So there's all sorts of interesting questions of how do you do this and how do you build this, and a lot of that's outside the scope of this class. But if you're interested, there's a lot that you could investigate here. Maybe you could think about doing a project on this sort of thing. There are lots of interesting results of this. So there's other examples we get into with that, with communication networks. One that kind of fits under this category, I don't know how well it fits under it, but you can also think of a search engine. So if you're building a search engine to compete with Google, probably not a good idea in general, but who knows. You're going to have to build a crawler that crawls through pages and captures information. And what you're going to have is you're going to have some vertices that represent pages, web pages, and then you're going to have edges, which are hyperlinks, so links from one page to another. And so you build out your picture of what this internet looks like by crawling through and keeping track of what pages you find and the links to other pages that you can find from that. And so you build a graph, really. And it's huge, obviously, but it's really just the same principles that we've already seen. So in principle, it's very simple. In practice, it's so huge that it creates all sort of problems about storage and how do you effectively use this information efficiently. One other example, you can have what are called citation graphs. These may not be something you run across or something that's interesting to you, but for academic papers, you can describe each paper as a vertex or a node, and then if one paper cites another, you can draw a connection between them. You can have an edge connecting them. And so you can build these citation graphs, and it's kind of like the idea of an influence graph, so it would be a directed graph, and it kind of gives you a sense of which papers are the most significant. So if all the papers in a certain field reference one paper, it's likely that that one paper is kind of the initiator. It's the one that is the most significant in that field. So we've got communication networks, we've got social graphs. A third application, which we'll talk about a little bit more later on, is transportation, which is very similar to the communication networks. It's the same idea where you're trying to carry something from one place to another, whether that's information in the communication networks, or in this transportation one, it's more like connecting, carrying people or goods from one place to another. So for example, you might have airline routes you could draw as a graph, trains, buses, etc. You could also do things we've talked about. Google Maps and other mapping software like that has to account for how to find a path from one place to another using roads that exist, using ways to travel that exist, and finding the most efficient route is a big problem. So we'll actually talk about how Google Maps does that. We'll look at the algorithm it uses, or at least a simplified version of the algorithm it uses, to answer that question, to find the shortest route between two places. There's also a famous problem known as the traveling salesman problem. You may have heard of this before. The traveling salesman problem says there's a set of cities that the salesman visits and has to visit in person, and the goal is to travel to all possible cities exactly once, using the shortest possible route. So that's the question, is how do you get through this whole list of cities with whatever connections exist among them? So you can draw different graphs to represent different sets of cities, and how do you efficiently travel to all of them using the shortest possible route? So you want to visit each city exactly once, and if you need to retrace your steps along one edge, well, you wouldn't do that because you're only trying to visit them exactly once. But the edges are not the significant thing. The significant thing is the nodes that you're visiting each of them. So with the Königsberg Bridge problem, the question was, can we traverse each edge exactly once? The traveling salesman problem asks, can we cover each node exactly once? Which is, a slightly different problem. So it might sound like the Königsberg Bridge problem, but it's different in that we're trying to cover all the possible nodes exactly once instead of all the edges. There's no general solution to this problem. So obviously, given a small example, you might be able to find a way to do this. But other than brute force, there is no general solution. So if you want to solve this, you would have to run through all the possibilities and then land on or select from all those tries the shortest one. But for any significant number of cities, that problem is prohibitively long. So there are approaches that will get you close to the shortest route. They'll get you a relatively short route, but there's no general solution for finding the optimal route. So there's a few examples of applications, very simple ones, and again, the applications are effectively endless. You can find applications in all sorts of fields. Anytime what you're looking at has significant connections, anytime the significant thing about your problem is connections among things, a graph is probably going to be useful to think about the problem in a new way.